Hello everyone and welcome to lecture today. Today we'll be talking about how to extend the idea of definite integration to multivariable functions. So we're going to start with two variable functions and talk about double integration. So let's review a bit from single variable calculus. So the definite integral of a single variable function, you'll recall, is defined in the following manner. So if we have a function of one variable, maybe it looks like this, from say some point A to some point B, we define and we can kind of call it the definite integral from A to B of that function, the accumulation of the function on the interval or over the interval from A to B. This is equivalent to thinking of it as the net area from A to B. So we have some function y equals f of x, and you'll remember from a Calculus 2 class that this is defined using what's called the Riemann sums. So we end up exactly mathematically defining this value by forming a partition of our region with n sub pieces under the function, which are actually rectangles, which we form by making the partition. This, say, is the first point in the partition, the second point in the partition, and so on and so forth, where there are n total points in the partition, and we approximate the accumulation by adding up the signed areas of rectangles under this function. So this means that we form our partition and then choose a sample point somewhere in each one of these subpartitions, and then look at the function value at each one of these sample points. This gives us a bunch of different rectangles, where the height of each one of these rectangles is the height of the function at the sample point. It could be positive or negative depending on whether the function is positive or negative. And we say that the approximation to the total accumulation of the function is the sum over all of these rectangles, the value of the function at the sample point, times the width of the rectangle. This is the so-called process of doing Riemann sums. And this summation approximates the total accumulation of the function over the interval from a to b. Let's include a couple more pieces of that partition here to kind of finish off this picture, this diagram. And if the what are called the upper sums and the lower sums, the upper Riemann sums and the lower Riemann sums, if the limit exists for both of those and is identical as n goes to infinity, we say that the Riemann integral is the limit as n goes to infinity of this Riemann sum. Because it's like saying as the rectangles get smaller and smaller and smaller, this value is the true value of the accumulation of the function, or the net area under the function from a to b. We always have to be careful to think of this as a net area, not an area, because if the function is negative, right, it's not the actual area under the function. It's the total amount of positive area minus the total amount of negative area under the function. The total amount of area of the function above the x-axis minus the total amount of area of the function below the x-axis. So this is why we call it a net area and not just an area. Right? It's to deal with the fact that most functions are both positive and negative. So the idea is that we have to take this one-dimensional definition of the definite integral. Now I can box this in a bubble. This is kind of like a review from a single variable calculus course. And we want to take this idea now and directly extend it to the idea of the definite integral of a multivariable function. So let's see how to do this. And we're going to start this by defining the double integral. Which is the same thing as the definite integral in 2D, or the 2D definite integral. So in this class, we'll focus on double and triple integrals, but you can actually do the integral, the definite integral of a function of any number of variables, and the definition is very similar in any case. So we'll start by defining the double integral. And the notation for this is following. We say that the two integral signs stands for the double integral of a function of two variables, then dA. And you also have to specify the region R that you're integrating over. So this is the notation for the double integral. And we'll kind of see why this notation is very important in a second. So this notation stands for the definite integral of a function of two variables over the region R. We can also call this, just like in 1D, the accumulation of the function f of xy over the region R. And we'll also see that this is a very nice interpretation as in a very, very similar manner to the 1D example. This is actually the net volume under the graph, or we'll say between the graph, of the function. So z equals f of xy in 3D. In much the same way that the single variable integral is a net area from a to b under, or we'll say between, the graph y equals f of x and the x-axis, which is y equals 0. The double integral of a multivariable function of two variables is the net volume under the graph z equals f of xy and the plane z equals 0. So this is one of the things that we'll see when we get into the applications of the definite integral. This is a very, very cool thing. So let's see how to define this. How do we define this? And the idea is just like we do in for the single variable integral. I'll say a very similar process to the single variable integral. This is called the process of Riemann sums. And the idea is the following, right? We have that we're trying to define the accumulation of some function of two variables over some two-dimensional region R. So we have some two-dimensional region R here, where we'll say maybe the minimum value of the region R here is A. The maximum value of the region R here along the x-axis is B. But we also have the y-axis that we have to look at as well. So we'll say the minimum value of this region R is C, and the maximum value of this region R is D. So just like before, we have to partition our domain into a whole bunch of small pieces, very, very small pieces, and then sample the function at sample points inside each one of these pieces. So the way that we do that can be very, very varied. The easiest way of doing it, just like in the 1D case, the easiest way of choosing the sample for this Riemann sum, and here we call the sample point CK, but I think what I might do is relabel this to XK star to denote the sample point, just because I think this is a better notation to denote that we're sampling points of X, so points from the domain. This is going to be, this point right here is X1 star, this point right here is X2 star, X3 star, and so on and so forth. So remember that the simplest type of Riemann sum is when we use a uniform partition. And that's when delta xk is just equal to the length of the interval divided by the total number of subdivisions in the interval. So the same thing is true for the multivariable case as well. But we'll just be as general as possible. So let's say we do a partition along x, and then we also partition along y. So what this looks like is that we end up cutting up our domain R into a whole bunch of pieces along x here, And similarly, we cut up the domain R into a whole bunch of pieces along Y. Let's include a couple more pieces in the partition to really show that. We can really do this and make really a very fine partition. And really we can get as accurate as we want in terms of cutting up our region into a whole bunch of very small pieces. So the idea here is that we have for a function of two variables, we have two separate variables that we have to partition for any domain that we're trying to integrate over. This is the first step in double integration, is forming this partition. And then once you form this partition, you have a whole bunch of different subrectangles. And if we say zoom in to one of these subrectangles, let's say we zoom in here to the kth subrectangle. This is going to be a rectangle that has a width of delta xk, which is the width of the rectangle in the partition, a height or a depth of delta yk, which is the height of the kth subrectangle in the partition. And I'll actually probably, instead of k, I'm going to use I and j. So specifically, we'll say we have, for each one of the partitions along the x-axis, we have that I, right, goes from 1 to n, where I is the point, the x point in the partition. So this corresponds to I equals 1, I equals 2, I equals 3, and so on and so forth. And same thing with the y-axis as well. We have a whole bunch of points, let's say we have the same number of partitions along y, so from 1 to n. You can do a different number of partitions along the y-axis, that's perfectly fine, but it makes it easier in terms of computation if we just use the same number of subrectangles along both x and both y. But so the idea is that each one of these subrectangles has a width delta xi and a height delta yj, and then we also have to choose a sample point. We'll call it xi star yj star in each one of these subrectangles. So each one of these subrectangles has some sample point chosen in it, in which we evaluate the value of the function at that sample point. So just like for a function of one variable, it's the same process really, just a little bit more complicated because the domains can be more complicated in 2D. The domains that we're integrating over. But we still, the Riemann sum procedure still consists of two steps. The first step, two main steps. The first step being that you have to choose a partition. And step 2 is that we have to choose a sample point. And then doing that, the Riemann sum becomes the following. It's Sn is going to be the sum over all of these rectangles, which is actually a double summation. It's a sum from I equals 1 to n of the sum from j equals 1 to n of the value of the function at the sample point times delta aij, where delta aij is the area of the sample point or the sample rectangle, the partition rectangle, I should say, of width delta xi and height delta yj. So this is the correct formula for a Riemann sum for a function of two variables, and it's directly, I shouldn't say directly the same because it's a little bit more complicated, but it's very, very similar to the Riemann sum formula in 2D for a single variable function. So for a function of one variable. Now it's really important for me to emphasize here that this is a double summation, right? Where in order to get this Riemann sum, you have to go through and you have to sum over all values of I and j from 1 to n. This is x 1 star, f at x 1 star, y 1 star times delta a 1 1 plus f at x 1 star, y 2 star, delta a 1 2, and so on and so forth, plus f at x 2 star, y 1 star, delta a 1 1, and so on and so forth. We have to do this procedure all the way until we get up to the function at xn star, yn star, delta a, and n. So in 1D, right, we only have a single sum in our Riemann sum. This Riemann sum has n terms in the sum. But in 2D, for a double integral, we actually have a much larger sum because we have n squared rectangles. If there are n rectangles or n terms in the partition along x, and there are n rectangles in the partition along y, then that means that this summation is going to have n squared terms in it, because you're going to have that many rectangles that you have to sum over in your Riemann sum. So it's a much larger sum than before. But the main idea here is that just like before, you can consider what are called the upper Riemann sums and the lower Riemann sums. And in the case of 1D, for a 1D integral, right, we say that if this limit exists, the limit as our partition gets finer and finer and finer exists, and the limit as n goes to infinity of the lower Riemann sums is equal to the limit as n goes to infinity of the upper Riemann sums, then we say that f is Riemann integrable. Well, we have for a double integral exactly what the Riemann sums are, and we have the exact same statement. Right? We say that if the limit as our partition in 2D of the Riemann sum formula, the limit of Sn, exists, and the limit of the upper sums is equal to the limit of the lower sums, then f is Riemann integrable. On the domain R. And specifically, we can evaluate the Riemann integrable, or the Riemann integral, by taking that limit. So if we have a nice expression for a Riemann sum for a function of two variables, the double integral of that function is just the limit of this Riemann sum as the partition gets finer and finer and finer, or smaller and smaller and smaller. Now the idea is that we're going to see there are much easier methods for evaluating the double integral than doing Riemann sums. Very often when you want to take the double integral of a function, you actually don't even consider the Riemann sums because it's too hard to deal with finding that Sn. That simplifying that into a closed form expression is often very hard, if not impossible, to do. Which is the same situation as in 1D for single variable functions. Typically in a Calculus 2 course, when you go over the integral, you see the definition of the Riemann integral, and then very quickly get into alternative means like the fundamental theorem of calculus and other methods of evaluating the integral, because it's not computationally feasible to do Riemann sums for even not even complicated functions, but for relatively basic functions it gets almost impossible to do. So there are much easier methods at our disposal. But the idea here is that it's very good to see this Riemann sum formula, and it also, it allows us to actually get certain results for certain and see certain results almost immediately if we know how to use it. So we will be coming back to it when we go into certain applications. It's also very useful for approximations. Sometimes you have a function that just, no matter how good you are with taking the integral, it's just too difficult or maybe even not possible to evaluate a closed form expression for the integral. So you have to rely on this Riemann sum formula if you want to do this and actually evaluate, or I shouldn't say evaluate, but approximate the integral. So the first function, and probably the simplest function to figure out the integral of, is going to be an important one for us because it's going to be a direct method that we use to calculate the area. So what I'll start with my first example is try to figure out what is the double integral of the constant function 1 over any region R. Or the double integral of the function f of xy over R when f of xy is just equal to the constant function 1. So by our definition of Riemann sums, this is the limit as n goes to infinity of Sn which is the limit as n goes to infinity of the double summation over I and j of the function, which is just 1, times delta aij. So what is this limit going to go to? Well, if we look at what Sn is, which is this double summation, right, the sum of all of the rectangles over the sum of all the rectangles in our partition, this double summation is just an approximation to the total area of the region R. So in the limit, as these rectangles get smaller and smaller and smaller, this should give us the total area of the region R. And this is exactly what we get when we take the double integral over any region. It gives you the total area of that region. This is the double integral of the function 1, the constant function 1. So in general, if you're asking to solve for the area of a specific region, you can do that by just taking the double integral of the constant function 1. More generally, if you take the integral of a positive function, and to visualize this, we're going to use the graph of the function in 3D. So let's say we have some region R, and a positive function defined in that region. So we know that this is going to be some surface that is going up and down on the region. So this is our region R. And this is our surface, z equals f of x, y. So it's the graph of the function f of x, y. When we partition our region R into a whole bunch of small pieces along the x-axis and then along the y-axis, in each one of these pieces we have a sample point, and at that sample point we take the value of the function. And so what we get is another rectangle, the height of which, a rectangular prism I should say, the height of which is given by the value of the function at that point. And the double integral is the sum of the function times the height of this rectangular prism times the area of the base. Right, so the Riemann sum is the summation over all of the rectangles in this partition of the value of the function at the sample point, which is the height of this rectangular prism, multiplied by the area of the base. So if the function is a positive function, then the double integral over the region R of that function is the limit as n goes to infinity of this Riemann sum. This Riemann sum is an approximation to the volume under the function, or under the graph of the function f over the region R. So in the limit as n goes to infinity, this Riemann sum goes to the exact value of the volume under the graph z equals f of xy over R. So this is how we can calculate. It gives us a method of calculating volumes as well. Now for a general function, this is going to be the net volume, because for a general function, the function could be positive or negative. But the idea here is that we can use this even if the function is negative to calculate volumes of contained inside surfaces. And we'll see an example of this a little bit later on. So a big question that we want to answer is how to evaluate. Double integrals. And the idea here is actually very clever. It's using what's called iterated integration. The main idea being that the double integral over region R, and we'll stick with a very simple region R for the first couple examples, because it turns out that the more general of a region R that we use, the more careful we have to be when determining the bounds of integration for a region. So we'll start with how to evaluate the double integral over rectangular domains. So we denote a rectangular domain in a similar interval notation to how we denote an interval in 1D. We say that a rectangular domain, say from A to B in 2D, consists of two intervals. The first interval is an interval along the x-axis, going from the minimum value of the domain to the maximum value of the domain, or from, say, A to B, and then from C to D along the y-axis. So this rectangle R is the simplest possible shape that we can integrate over. So this is what we'll start with in terms of evaluating an integral. The idea is that the double integral of a function can also be written as the double integral from A to B in x, from C to D in y of that function. Notationally speaking, we can say then that dA is the same thing as dy dx. So this is the notation that we use for integration over rectangular intervals, where x goes from A to B and y goes from C to D. Now it's very important to remember the order here. If you don't order the bounds correctly, then you might calculate the wrong value. The outer bounds of integration always have to be with this outer variable. So this dx here is connected in some sense to these bounds A to B, and this dy here is connected to these bounds right here from C to D. You don't always write the following, but it's a good idea to maybe get in the habit to do this the first couple of examples that you do of a double integral, because this notation right here really means something very specific. It means calculate an iterated integral. So you calculate the integral from A to B of the integral from C to D of the function with respect to y. And then the result that you get from this integration, you do the integral of the function from a to b. So we don't always write these boxes here, but it's nice to write this at least a couple times. Whenever you see this iterated integration, the innermost bound of integration is connected with the innermost variable here. This is called the inner integral, or the inner iterated integral. And then the outer integral, or the outermost iterated integral, is this x integral, is the outer integral. So the idea is that when you're determining the bounds, you want to start from the outside and move in. And then when you evaluate the integral, you want to do the innermost integral first and move out. That's kind of like a reverse procedure. Determining the bounds, you start with the outer integral and move in, and then when you evaluate the integral, you have to do the inner integral first and then move out. And this may not seem too important for rectangular domains, and it turns out it's not. When we talk about what's called Fubini's theorem, right? Fubini's theorem will tell us that we can do a given rectangular integral in any order that we want. However, we have to be a little bit more careful when we're talking about more complicated domains. We can still choose any order that we want, but determining the bounds for a non-rectangular domain is often very difficult. So we'll see how to do this correctly when we get to Fubini's theorem. But let's go through and do a couple examples of an iterated integral over a rectangular domain, just to kind of get that nailed down and get it specific for a couple different examples. So we know how to do this. So we take the double integral from 1 to 2 and 3 to 4 of the function x squared plus y squared plus 2xy dy dx. Now this is the same thing as the double integral over the region R of the function x squared plus y squared plus 2xy. And really, if you want to draw a picture of this, we're taking the accumulation of this function over the rectangular domain for x from 1 to 2, and then y from 3 to 4. So the value that we get here, this is our region R, and the value that we get when we evaluate this is the total accumulation of this function inside this rectangle. So if we go through and do this, we do the inner integral first. The inner integral is the integral with respect to y of this function. So we integrate this function with respect to y, and we know that from calculus 2 that the simplest way of doing that is finding the antiderivative of this function, and it's with respect to y. So the inner integral, it's similar to doing the partial derivative. When we're doing the inner integral with respect to y, and we're searching for the antiderivative of this function with respect to y, we treat x as constant and proceed to take the antiderivative. So if x squared is constant with respect to y, so the antiderivative of it is going to be x squared times y. Antiderivative of y squared is going to be y cubed over 3 from the power rule. And the antiderivative of 2xy is going to be 2x times y squared over 2. And then from the fundamental theorem of calculus, we have to evaluate this at our y bounds. And when we do this, we get 4 times x squared plus 4 cubed over 3 plus x times 4 squared minus 3x squared plus 3 cubed over 3 plus 3 cubed times x. Which simplifies to the following. It'll be x squared plus 7x plus 37 over 3 when you go through and simplify this expression right here. So once you do that, once you do this simplification, this is what you get. The double integral reduces. So we've done our first integration right here. It reduces to the single variable integral of this function from 1 to 2, which we can evaluate by, again, going through and finding the antiderivative of this expression, which is x cubed over 3 plus 7x over 2, x squared over 2, plus 37 over 3 times x. And when we plug in our bounds here from 2 to 1, this becomes 2 cubed over 3 plus 7 times 2 squared over 2 plus 37 over 3 times 2 minus the lower bound plugged into this function, which is 1 cubed over 3 plus 7 times 1 squared over 2 plus 37 over 3. And so this simplifies when you go through and do the arithmetic here and simplify everything down. This number just simplifies to 151 over 6, which is the exact value of this double integral. This is approximately equal to 25.16. So there you have it. This is the exact value of this double integral. So it's the accumulation over this rectangular region R of this function. And because the function is positive, this is actually equivalent to the volume under the region, under this function, over this region, over this rectangular region. So this is a very, very powerful idea. We'll do one more example to kind of show that we can directly go through and use these iterated integrals in a very nice fashion. So let's just consider the double integral for x from 0 to 1, y from 0 to 1 of the function x times cosine of xy. So the inner iterated integral here is the iterated integral from 0 to 1 of this function with respect to y. This is our inner iterated integral. And we can go through and evaluate this right away. The x is constant with respect to y, so this comes out of this integral. And we're just left with the antiderivative of the function cosine of xy, which is going to be given by the function 1 over x times sine of x times y. This is the antiderivative of the function cosine of xy with respect to y. Because if you take the derivative of this expression with respect to y, you're going to get this cosine of x times y here. So we have to evaluate this from 1 to 0. The x times 1 over x becomes 1, so that cancels out. And when we plug in our y bounds here, this is going to become sine of x times 1 minus sine of x times 0, which is sine of 0, or 0. This is just equal to the integral from 0 to 1 of sine of x dx, which is the antiderivative, or negative cosine of x, of this function, evaluated at the upper x bound and the lower x bound, which is going to be negative cosine of 1 minus negative cosine of 0, or 1 minus cosine of 1. And this value is exactly the correct value of the double integral of the function x times cosine of xy over this region R. That's the accumulation of this function over this region. So this is the method of doing iterated integrals over a rectangular domain, and it's our starting point for how we're going to be going through and thinking about evaluating the double integral of these functions over many different types of domains. So I think we'll consider one more example just to kind of bring this home and kind of show that we can use this procedure to get many different types of geometric formulas that are analogous to formulas that we might obtain in a 2D setting for 2D geometric properties. And what I'll ask you to remember is that if we have, say, any trapezoidal figure, say for instance, we have a trapezoidal figure that looks like this in 2D. The area of this trapezoidal figure is given by the width of the base, or the size of the base, multiplied by the average height. So the height at the midpoint right here of this trapezoid is, we'll call it h. It's this width of this trapezoidal figure times the average height between the lowest point in the trapezoid and the highest point in the trapezoid. So it turns out that we actually have a very similar formula for, in 3D for the volume of a trapezoidal shape with a rectangular base, or with a square base. And we can prove this directly, figure out what this formula is directly using the double integral. So suppose that we have some rectangular base here to our trapezoid. It's a trapezoidal prism, say, we could think of it as. And specifically, let's say that along the y-axis, this base goes from C to D on the y-axis, and it goes from A to B on the x-axis. So it's a rectangular base, the top of which is given by a plane. Right? Any trapezoidal prism has a top which is going to be given by some plane. So the top of this trapezoid is a plane, therefore it's going to have the equation z is equal to mx plus ny plus L. And we're going to assume that the values m, n, and L are giving us a plane that is above the xy plane. So you have a picture that looks like this. Even if you don't, you still have the net volume under that plane, but we just want to get a general formula that's similar to the equation in 2D, for a trapezoid in 2D, but for the volume of this plane. So if z is positive, then the volume under this plane, or the volume under z equals mx plus ny plus L, is exactly equal to the double integral over this region. So it's the double integral over the region R of mx plus ny plus L dA, or in terms of our exact bounds, it's the double integral as x goes from A to B, as y goes from C to D, of mx plus ny plus L dy dx. This becomes the double integral, the integral from A to B, from C to D. And we can directly go through and do this first iterated integral. It's the antiderivative of this function with respect to y, which is going to be mx times y plus ny squared over 2 plus L times y, evaluated from D to C. And then we still have to take the outer integral of this function, but let's simplify it a little bit first. So when we plug in our bounds C and D, we get the integral from A to B of, this will be mx times D minus C plus n over 2 d squared minus c squared plus L times d minus c. This is what we get when we plug into that fundamental theorem of calculus. We plug in our upper bound and we subtract this function plugged in with our lower bound. And we can even do some cleaning up here and some more simplification. So before we do this integral, remember that d squared minus c squared is the same thing as d plus c times d minus c. So we can factor out d minus c from every term on this expression. So this integral will be the same thing as d minus c times the integral from A to B of mx plus n over 2 times d plus c plus L. It's always nice when you can sort of simplify things as much as possible. So when we go through and do the antiderivative of this expression, we get that this is going to be mx squared over 2 plus n over 2 times d plus c times x plus L times x. Because the integral of mx is mx squared over 2. The integral or antiderivative of n over 2 times d plus c is constant, so it's going to be n over 2 times d plus c times x. And same thing with L here, the antiderivative of that is going to be L times x. This will be equal to d minus c. When you plug in the bounds for x, you have m over 2 times b squared minus a squared plus n over 2 times d plus c times b minus a plus L times b minus a. And notice again that we have another thing, we have this b squared minus a squared, which is the same thing as b plus a times b minus a. So I can factor out a b minus a from every single one of these terms in this expression, which gives me d minus c times b minus a times m over 2 b plus a plus n over 2 d plus c plus L. And this value is the value of the volume. The volume under z is mx plus ny plus L over this rectangular region R. This is equal to d minus c times b minus a times m b plus a over 2 plus n c plus d over 2 plus L. And what this formula is telling us is a direct analog of the previous formula from 2D for a parallelogram, because it's telling us that this d minus c times b minus a is the area of the rectangular base multiplied by the height of this trapezoidal pyramid at the midpoint. Okay, this value in parentheses right here is the height of this triangular pyramid at the midpoint, because b plus a over 2 is the midpoint, the average value of this base in the x, along x, and this is the average value along y, or along the y-axis. So this value, its height at the midpoint, is exactly the height at this point right here, at the midpoint of the parallelogram, or the height at this point right here. So if this right here, this height right here is h, and then a is the area of the base, we're seeing that the volume of this trapezoidal pyramid is going to be this area of the base times this height right here. which is a direct generalization of our previous formula using the double integral. I think this is a very cool example to end the lecture with, because it shows us that we can actually derive very general formulas for geometric shapes using the double integral. And we'll see how to expand this in the next lecture when we consider some properties and more detailed examples that use non-rectangular domains. And that will be essentially explained in the lecture after that when we talk about Fubini's theorem. But thank you very much for coming to lecture today. I hope you all learned something and had a great day.